take a look at some polynomial theorems which basically save us time. I mean, polynomial division is fantastic, but depending on how big the polynomial is, it can take a lot of time. So the first thing is the remainder theorem, because sometimes all we're interested in is what's the remainder. So how can we find that remainder without actually having to go through the whole division? What actually ends up happening is, if you're going to divide by a linear factor, x minus a, the remainder turns out to be what you get when you substitute a in. Now the reason that's useful is because all polynomials can be broken down to linear factors. Well, using real numbers, it's a combination of linear and quadratic. But once we start thinking about complex numbers and imaginary numbers, they all can be linear. So we can always work out what a remainder's going to be. So let's just prove that. So there's our polynomial division. If I substitute in the divisor being x minus a. So, all right, it's now x minus a times the quotient plus the remainder. We want to show that polynomial a is in fact that remainder. So if I substitute a in, then obviously in the first term, a minus a becomes 0. So polynomial a is remainder a. Now we want to show it's remainder x, not remainder a. But we've just divided by a linear factor. And we said the remainder is always of order less than the divisor. Therefore, the remainder must be of order 0, which is a constant number. So if it's constant, well, remainder x and remainder a are the same thing. So polynomial a does become the remainder. Okay. So there's a little proof. So we want to find out this remainder. So rather than doing the whole division, I can just substitute in 2 and I get negative 19. I know what the remainder is. Okay. Now where this becomes really useful is when, instead of calling it the remainder theorem, we call it the factor theorem. Because if that remainder turns out to be 0, then we know x minus a is actually a factor. It'll go in it precisely. So that's basically what the factor theorem says. Oh, well, if we divide it by x minus a, and that remainder turns out to be 0, we know it's a factor. Now, it turns out x minus 2 is going to be a factor of this polynomial. They want us to go and factorise it. So let's just confirm it is, sub in 2, and sure enough we get 0. Now, the stupid thing about this sort of question, because the factor theorem is meant to save us time, so we don't have to do a polynomial division. But now I've got to factorise this whole thing, so I've got to find the other factor. So I've got to do a polynomial division. Seems stupid. But all right, let's do it. X minus 2 in there, subbing in x and x cubed, and bring it down, and plus 2. Okay, we're getting there. Oh, look, minus 15. Remainder 0. So the stupidity of doing it this way is that, well, why did I bother using the factor theorem if I'm going to end up doing a polynomial division anyway? The polynomial division also shows there's no remainder, so I didn't need to use the factor theorem. I might as well just done the division. So the logic actually is the reverse. It's actually the division that was the waste of time, not the factor theorem. All right. Oh yes, so whether I complete my factorisation, because that quadratic does factorise nicely. I know x minus 2 is a factor, but there's a little bit of logic here, because what is factorising? It's the reverse of expanding. Now if I was going to expand out, I would have got all the terms and multiplied them by each other. So to get the leading term here, I would have gone x times something in here and got x cubed. So all I've got to do is ask myself, x times what is x cubed? And I know the leading term in the second parenthesis. So what I'm basically saying is, well, the leading term times the leading term, which is missing at this stage, will equal the leading term. So I know x times the missing leading term will be x cubed. So that missing leading term must be x squared. I can do the same with the constant. Okay, so, because the constant in this first one, that negative 2 times the missing constant in the second one, would give me 30. Well, therefore that missing constant, logically, is minus 15. So there's my factorisation at this stage. I'm missing the middle term there, the x. So the question is, how many x do I need? Well, at this stage, if I was to expand that out, I'd get minus 15x. I want minus 19x. Therefore, there's a missing. So what I was saying is, if we expand out now, how many x would I have? Minus 15x. How many do I need? Minus 19x. So there is a missing minus 4x. So therefore, this missing term times negative 2 must be minus 4x. So the middle term is 2x. And I've got to factorise. So I guess that's what we call factorising by inspection. It's often a lot quicker than just doing a polynomial division and so on. You are right, you could use the factor theorem multiple times. That's assuming that second one factorises. Yeah. So, which it does in this case, as we saw before. So there's our final factorisation. All right, let's have a look at this one. This time they haven't given me any hints. Well, there's an infinite number of numbers we could sub in. But obviously only some are logical. Because we know the constant times the constant will give the constant. It makes sense to try factors of 36. So that narrows down from an infinite number to quite a few less. All right, well, the factors of the constant. I deliberately picked 36 because it has quite a few factors. So it might be 1, 2, 3, 4, 6, 9, 12, 18, 36. Still got a lot to try. Which one would you try first?
1.
Yeah, I think I would too. Go for the easy one. By the way, if one doesn't work...
Negative 1.
Well, no, what I'm getting at is if one doesn't work, 36 is probably a stupid one to try. Because you would have gone 1 times 36. So I wouldn't try 36 next. They could have been negative as well. So negative 1, negative 2, negative 3. And if it's monic, they're all the possibilities. But because it's not monic, one of the factors is not going to be x minus something. It might be 2x minus something. So therefore, we have to try all the factors of the leading coefficient. Could be in the denominator. Because if you think about it, if 2x minus 1 was a factor, you'd get the answer x equals a half. The top of the fraction is a factor of the constant. The bottom of the fraction is a factor of the leading coefficient. So, we could also have a quarter, 2 quarters, 3 quarters, 4 quarters. I'm going to cross a few out just to save time because, of course, 4 on 4 is 1, and that's already on my list. Phew, there's 3 less we have to try. Now the halves, all the ones on 2. Again, some of those are repeated, so let's cross out the repeats. There's all our possibilities. Oh, but hang on, they could be negative as well. So we've got a handful of numbers to try. So which one would you try first?
4.
Of course you would. Now, let's try 4. Oh, that works. Outstanding. All right, so I know x minus 4 is a factor. Let's continue the factorisation. Leading term times leading term must give me leading term. So x times something gives me 4x cubed. That's got to be 4x squared. Constant times constant gives me constant. So negative 4 times something will give me 36. Negative 9. I've got a missing term in the middle. Now, I could use either the x's or the x squareds to work this one out. I've got 2 possibilities. Let's go with the x's. At this stage, I have minus 9x. Oh, hang on. I want minus 9x. That implies that's it. If you're not sure, check the x squareds. At this stage, x squareds, we've got minus 16x squared. Sure enough, yep, that looks good. So there's our factorisation, but of course the second one is the difference of 2 squares. So we could do 2x plus 3, 2x minus 3. So I still maintain that's quicker than going through a polynomial division, which uses a bit of logic to work out those numbers. HSC question. So they've told us the divisor is x plus 1, x minus 3, which is a quadratic, of course. So the remainder would be a linear function, which they've written in a rather strange way. rather than just writing it as ax plus b, they've written it as ax plus 1 plus b. Now, that's still a linear function if you think about it, but I'm sure there's a good reason why they did that, and we'll discover it as we go through the question. Possibly this is why. When the polynomial is divided by x plus 1, and x plus 1 of course is a factor of the a as well, we know the remainder is minus 11. Divided by x minus 3, the remainder is 1. What's the value of b? Okay. We know polynomial negative 1 is negative 11. Oh well, there's b. We've got it straight away. Because they've written it in this way, subbing negative 1, that becomes 0. Subbing negative 1, that becomes 0. So b is negative 11. What's the remainder when it's divided by the actual quadratic? Oh, well, now I've got to work out a. The other piece of information they told us, divided by x minus 3. Polynomial 3 is equal to 1. This time when I sub in 3, the first part becomes 0, but I get 4a plus b is 1. But we just worked out b was negative 11. So a is 3. So my remainder is 3x minus 8. In other words, it's the 3 lots of x plus 1 minus 11, but when you tidy that up, you get 3x minus 8. 2002 paper. Suppose that this cubic is equal to x plus 2 times some polynomial plus 3. Find the value of a. Oh, using a clever substitution, we should be able to find a. What shall we substitute in? Yeah, negative 2 would be the logical thing, because then on the right hand side we get 0, and so it doesn't matter what quotient x is, and we can get it straight away. So polynomial negative 2 will end up being 3. I suppose another way of looking at that, you could say is, well hang on, the remainder is 3 when I divide by x plus 2, so using the remainder theorem. But either way, sub in negative 2 and we get 3, that's what we know. And a is 19. A is 19. Oh, getting an older question now, 94. Okay, we divided by a quadratic this time. What is the most general form of the remainder given by remainder x? Oh, y. They're giving me the answer. Right, explain the answer. Why is that?
Because the remainder has to be of a lower degree of divided.
Yeah, I mean, we know we're being dividing by a quadratic. Has to be lower. It might be a constant, but we don't know. So the most general form would be a linear function. A might turn out to be 0, but so the most general form would be ax plus b. So that's the sort of thing they're looking for. Well, the degree of the divisor is always more than the degree of the remainder. They've told us polynomial 4 is negative 5. Show that remainder 4 is also negative 5. Okay. Well, if we write out our expansion, the divisor was x plus 1, x minus 4, times the quotient, plus the remainder. They've told us polynomial 4 is negative 5. So subbing in, 4 minus 4 of course is 0. So remainder 4 is polynomial 4, which they've told me is negative 5. Further. When it's divided by x plus 1, the remainder is 5. Now let's find the remainder. So remainder 4 is equal to negative 5. We know that. So the remainder, ax plus b. So 4a plus b is negative 5. We know that. They've now told us that when we divide by x plus 1, so polynomial negative 1 will be 5. Sub in negative 1, I get minus a plus b is 5. Just got basically a couple of simultaneous equations. Quite an easy one there. The b's will cancel. A is negative 2. Therefore, b is 3. We said the remainder was ax plus b. So the remainder is minus 2x plus 3. Ooh. Oh, that's what I was talking about before. This, in number 3, it must have a factor of 2x minus 1. So when you're using your factor theorem, use a half to prove 2x minus 1 is a factor. Because basically you're saying what makes it equal to 0. So 2x minus 1, a half would make that equal to 0.